one common AI task is spam filtering. So you get a bunch of emails, and the goal of this task is to classify emails into spam or not spam. Okay, and you can take two approaches to this. One is the rule-based approach, and one is the machine learning approach.
Right.
In the rule-based approach, what you're trying to do is handcraft specific rules that the program will follow to determine whether an email is spam or not. So in classical programming, which is the rule-based approach, what you do is you create a program, you feed in the rules and the data, and you get the answers out of it. The answer in this case being like spam or not spam.
Right.
Okay. But in machine learning, what happens is you feed the data and the answers into the machine learning program, and as the output, you get the rules. So, hey, welcome to the Art and Science of AI. You're listening to Season 1, which we recorded in May 2023 as a continuous 3-hour-long conversation. Season 2 is now live, so if you're enjoying this discussion, please subscribe for new episodes every week. So do you want to get started?
Yeah, let's do it.
So I think the first thing I want to talk about is what is artificial intelligence? And like one definition I looked up is that basically it refers to computer systems that are capable of performing tasks that typically require human intelligence. So like anytime a computer program can do something that you think requires human intelligence, that's what we call AI. And it's a pretty vague definition. Calculator AI, like initially probably, yes, you would call a calculator AI. Before we had calculators, people would have considered that to be AI. But the moment like that becomes easy to do, that's no longer considered AI. So it's kind of always like a moving target. Every time something becomes easy for computers to do, people start thinking that's no longer AI, that's just normal like computer program. Like even if you think about like computer games, basic computer games that we have, when you interact with computer opponents, like maybe there's a car racing game and there's a computer that's racing a car, that is AI. Like the computer is driving the car on the game. But today, like we don't really think of that as AI because
so you're trying to say that AI has been here for a while. It's just that it's like in our general consciousness, the word AI is like been increasingly popular recently. But like in some sense, AI has been around. Like all of these things are AI.
Yes, and if you go far enough back, you can think of any kind of technology as in some sense AI. Like before we had calculators, we probably had like an abacus, and the old like thing that you move beads on, like that's a rudimentary form of AI. So it's just a matter of advancement, and I think it's always a moving target. AI is always referring to the next big thing that computers can't do right now.
Right.
So anyway, we're right now going through like a revolution where AI programs are doing more and more than ever before. But I think it's helpful to break down the different like approaches to, before we think about machine learning and what machine learning is, let's just think about two broad approaches to how AI can be approached.
Yeah, I mean, what is machine learning in relation to AI? First of all,
so machine learning is a particular approach to AI. That's basically it. Like AI refers to doing any tasks that require human intelligence.
And machine learning is one of the ways to
is one particular approach. And in fact, there's a nice graphic that I found that explains this, which is AI is this big thing. There are two broad approaches to AI. There's what's called rule-based systems, and then there's what's called machine learning. And we can go into the differences between the two. And within machine learning, a subset of that is neural networks, and deep learning is another subset of that.
Yeah, I've heard all of these terms, but I mean, it was like, okay, these are some things about AI, but okay. So these are all approaches to...
These are approaches, and you can see the relation here of which is a subset of which one and which is mutually exclusive. And everything that today is really popular, ChatGPT, Midjourney, what you were talking about, most modern applications are within this little deep learning circle over here. So that's the approach that's become most popular.
So are you saying like if like this is the stuff where I have been super fascinated, and to understand this and to fully appreciate it, it's like the approach I should take is to understand how we came to this?
Yeah, I mean, I don't know if like that's the approach you should take. If you want to understand the general foundations, yes, that's how I would.
Yeah, I like that. Okay.
Yeah, I mean, there are also other approaches to this. Like, for example, one of my favorite AI educators, his name is Jeremy Howard. He has a course you can take online. It's called Fast AI. And he has the opposite approach. He's like, he has a course that starts with deep learning. He says, forget about understanding all this stuff. It's called Practical Deep Learning for Coders. And he just gives you some high-level Python libraries that you can use to start building deep learning applications right off the bat. So that's one approach. I think if you want to go and build something, that's a better approach. If you want to understand things, like, it's useful to have some theory.
Yeah.
So one thing, before getting into machine learning, it's useful to think about this distinction. In the early days of AI, like until about the 1980s or so, the rule-based system was the most popular approach to AI. And to understand the difference between these two approaches, we can consider a simple example of an AI task. Think about spam filtering. So one common AI task is spam filtering. So you get a bunch of emails, and the goal of this task is to classify emails into spam or not spam. Okay, and you can take two approaches to this. One is the rule-based approach, and one is the machine learning approach. Right. In the rule-based approach, what you're trying to do is handcraft specific rules that the program will follow to determine whether an email is spam or not. And you might have rules that, hey, if it doesn't have a subject. Yes. Yeah.
But I understand what you're trying to say.
It could be like
something, then it's a spam.
It's basically a series of like if-then clauses. It's a logical structure. You can say if it has the word lottery winner in it, if it has the word
Nigerian prince.
Yeah, exactly. Classify that as spam.
Yeah.
Otherwise, it's not spam.
Yeah.
So that basically the original approach to AI was building increasingly complex rule-based systems to do these kind of tasks. So going back to the computer gaming example that we talked about, like if you want to drive on a racetrack, you can program explicit instructions and say, like, if you are, check all these conditions. If you're this much distance away from the wall, if you're this much distance away from the racer, then accelerate, otherwise brake. But giving very explicit rules, that is the rule-based system.
Right.
Whereas the machine learning approach is something completely different. That's where you said that I'm not going to define the rules. I'm going to let the program discover the rules based on a bunch of data that I'm feeding it. And we'll talk about how that works, but at a high level, that's the distinction between these two approaches. And the rule-based system is what I spent a lot of time studying when I studied logic. The original approach was that we could get smarter and smarter AI systems by making smarter and smarter rules and understanding the world better. But it turned out that approach kind of hit a dead end, and it didn't have that much power. And the machine learning approach is really what gave AI systems a lot more power.
Right. Yeah. I remember I was watching, like, back when, it's not that AI has been popular in all of our general consciousness only very recently. It's been like 5-6 years. Yeah. And I took my first attempt like maybe 5-6 years ago, and there was a very nice explainer video by like one of the Google associated channels, and they were trying to explain exactly this, is like, how does machine learning really work? And the example they took was, imagine if you had to create a program that identifies oranges. Okay. There are two approaches you can take. One approach is a rule-based approach where you say, if the color of the thing that you're seeing is orange, and if it's round, and if the texture is like a little grainy, then it's an orange. But hey, imagine what happens if someone submits a photo of a black and white orange. Like, we as humans would be able to identify and say it's an orange, but your program has just failed because it doesn't meet your first rule that it should be orange in color. And that's a problem with rule-based approaches. Like, you will always find some area where like one of your rules fails, but like we as humans don't have those like rigid rules.
So absolutely. The world is just too complex. Like, even in the spam example, the original approaches were like they would filter out keywords.
Correct.
And then you say that, okay, like $1 million lottery is filtered out. But what if I'm just genuinely writing an email to you?
Imagine missing out on $1 million because you actually...
Or it could just be that I'm making a joke. I'm like, hey, I read this article about $1 million lottery. It could be any number of things. But yeah, it's too complex to like model, and these systems have always failed.
Right. As the complexity increases, rule-based models hit a plateau sorts. Okay. Yeah. That makes sense.
So one good way to think about what is the difference between machine learning and rule-based systems is this diagram, actually, which I really like. I saw it in one of my machine learning classes at university, and it really helped me understand what is machine learning. So in classical programming, which is the rule-based approach, what you do is you create a program, you feed in the rules and the data, and you get the answers out of it. The answer in this case being like spam or not spam.
Right.
Okay. But in machine learning, what happens is you feed the data and the answers into the machine learning program, and as the output, you get the rules. So that's like the key difference between these two approaches. In one case, you're explicitly providing the rules. In the other case, you're providing the answers and you're getting the rules as an output of that.
Right.
So that, I would say, is the key difference, where you're saying, I'm not going to try to learn what are the rules here, what distinguishes spam from not spam. I'm just going to provide a bunch of data and let the system figure out what are the underlying patterns in that data.
Right. And I mean, the ultimate goal in both scenarios is actually to get to answers, like, because the ultimate goal is to provide an input to the system and be able to determine if like put it under a model and see if you get an answer or not.
Yes. I guess you could make a distinction here between, within answers, you can say like known answers and unknown answers. So in the machine learning terminology, we call it training data and validation data. So like, training data is like what I train the model on, and then I have to go and test or validate it on data that it hasn't seen before. So, I might have a set of like maybe 10,000 examples of spam and not spam emails, and that's what I'm calling answers here. But my ultimate goal is to go and use this on emails that have not yet been written, emails that are going to be written tomorrow or next year, and apply the same rules to those emails.
Right.
And
that makes sense.
That's the ultimate goal. So I think then we can talk about some of the basic concepts of like what is a model to start with, like, because the output of machine, like ultimately with a machine learning system, what you're going to get is like a model that will predict new answers for you. And the definition of a model is basically it's a representation of a system or process that can be used to make predictions. That's ultimately what you're trying to do, make predictions about the future.
So if I understand the way you're going through this correctly, so what you said is somewhere in the 1980s, folks realized that the classical programming approach hits a wall. And if we need to make advances in computer science or just advances in our original pursuit, which is to make our systems more human intelligence, then we need to take a different approach. And that approach turned out to be machine learning, is what you're saying. Okay. So now advances started happening in the machine learning field. So the genesis of this field was somewhere in the 1980s, and so we'll get into that now. Like, what are some...
and most recent advances, neural networks and deep learning have seen the most advances in the 2000s in this century, and particularly in the 2010s, I think, because the scale of computational power and data that's needed to make them very useful has only recently emerged. And before getting into neural networks, let's talk about, I'll start with what I would call classical ML. That's like machine learning that works, pre-2000, let's say. It didn't need a ton of data and a ton of computational power.
So, and you're saying to understand that, even the classical ML approach, you have to first understand what training data is, and then I think you were getting into what...
or like, what is a model to start with?
Actually, let's start with that.
I came up with a list of like, what are 5 components of like what a model is.
Okay.
So these are 5 things. This is a simplified view. There are probably more things, but you need to know what is the model architecture, and you need to know what are the features of the model. And then the model will have parameters. It'll have an objective function, and it'll have a training algorithm. And if you have all these 5 things, you have a model that you can use to go make predictions about the world and go, predict whether an email is spam or not spam, or whatever task that you want to do with it.
You're saying ultimately a model is a prediction making engine.
Yes.
Okay.
Yes, it's a prediction.
That's a good way. Okay.
Engine.
Okay, I understand. And then these are the components typically that go into building a model. Okay.
And so I think I wanted to start with a simple example of a model. One of the most simple machine learning models is called linear regression. We can start with that, and we'll take a
very scary sounding name.
But it's
can you make it like accessible for me?
So this diagram, I think, does a pretty good job of making it accessible to you. It's just basically a line. It's a line on an XY plane. That's what regression is. So basically here, what you're trying to do is, the task here is to predict the price of a home.
Okay.
Okay, that's the
Okay.
task. You're like given a home, predict the price. And
What do you mean given a home? Like I see a home?
yeah, usually you would have a data set with a bunch of houses listed on it, but you could think about it as like Zillow, right? How does
Okay.
Zillow work today? When you go on Zillow or Redfin,
if given certain features about a
Yeah.
home, can I predict the price of the
Zillow
home?
will give you this thing called a Zestimate, right?
Right,
It tells you what it, yeah.
Right.
And the Zillow Zestimate is way more complex than what we're going to talk
It's
about
also
here.
absurdly wrong or whatever.
Huh.
It's we can get into that. I have a conspiracy theory is that the Zillow estimate actually ruined the real estate market for everyone. Zillow estimate and the Redfin estimate.
Okay.
Yeah. Anyways.
Okay,
We don't have to
we
talk
can
about
talk
it.
about that.
Yeah,
Or maybe we can talk about it after this example. I'm curious why you think that.
Yeah.
So in this very simplified example, there's only one feature we're using, okay, to predict. And this feature is called number of rooms. So just assume it's very simplified. We say there's just one feature I use and I'm going to predict how much the house costs. It's probably going to be inaccurate, or maybe in a world in which you restricted it to like, I'm only looking at homes within a certain area where all other things are fixed, you might say that
I agree with you. I think like if you had to take like one thing as a predictor of the home price, like one basic thing to start with,
you pick square footage, or
it's not going to be right, but it's a good indicator. Yeah.
So the only reason I picked this example is to like explain like what these things mean here.
Got it.
So model architecture, that just means like, what is this model? It's like the underlying structure of the model. And in this case, the model is just this equation that says price equals 100 plus 50 times the number of rooms.
Okay.
Because that's the line that fits best with the existing data we have.
Right. Okay. So you're saying you have some existing data.
Yeah.
With a bunch of houses with the number of rooms in those houses.
These are the data points.
And the prices of the houses.
Yeah.
You plotted them on this line.
No, you plotted them first, and then you tried to find what is the line that best fits those data points. Yeah.
Right.
So we covered the first thing. That's the model architecture.
Okay.
Features, as I said here, the feature, there's only one feature. Feature is basically the input variables or like the attributes that you consider of individual data points. And here in this simplified example, there's just
number
one feature.
Of rooms
is the feature. Is the feature.
Right.
Yeah.
Sorry, go back to your previous slide. So model architecture is in this case linear regression.
Linear regression, yeah.
Because it's like one line.
Yeah.
Right?
Right.
And features is a number of parameters.
No, parameters is different.
Oh, sorry, my bad.
Features is the input characteristics.
Okay.
Yeah.
Okay.
So next is parameters, actually. So this model has two parameters. You can see them here. The number 100 and the number 50 are the two parameters of this model.
Okay.
So 100 is called the intercept, and 50 is called the coefficient of the first feature.
Okay.
So in generalized way, you will say that y equals b plus like beta 1 x1 plus beta 2 x2. That's the linear regression formula, where for every as you add more features, you'll get more parameters.
Right.
Each feature will have its own coefficient.
So the parameters scales with the features.
Yes.
Is it a 1-to-1 ratio?
In the case of linear regression, yes, it is 1-to-1, but no, often it's exponential. And then when we talk about GPT-3, remember GPT-3 has 175 billion parameters. This model has 2 parameters. So I want to build up some of the intuition here.
Okay. Yeah, actually, I've heard this before. GPT-4 has 1 trillion parameters. GPT-3 has 107. So I want to know, how do I think, like, okay, 1 billion and trillion is a cool number. Like, I understand, like, oh, something big is happening.
Yeah.
But how do I think about this? Are you saying that every time I'm talking to GPT-4 versus GPT-3, when I ask GPT-4 a question and when it answers me, it looks at 1 trillion things every time?
175 billion. Yeah.
GPT-3 looks at...
Just start with this example first. Every time you interact with this model, you give it a home. By giving it a home, that means you just input the number of rooms. And you ask it for the answer.
Right.
It's calculating 2 parameters and giving you the answer.
Right.
It's saying it's doing...
But in this case, my input is scaling with the number of features, right? Like in the case of GPT, the input is a simple prompt.
Oh, yes, but actually internally there could be a lot of things. So for example, the features don't have to correspond to the inputs. I could create a feature called the square root of the number of rooms.
Got it.
Yeah.
Okay,
and if suppose I have 2 features like number of rooms and square footage, using those, I could create like many more features. I can say the product of the square footage and number of rooms is another feature.
Right.
The square of the number of rooms times the cube of the square footage. So I could create like, 100 features with just those two inputs, and that
Right.
would have 100 parameters. So
Right.
that's often there's a balance. Like as you increase the number of parameters, you can get more predictive power, but you have to find the optimal number of parameters. Sometimes if you have too many parameters, you might overfit the data. You might just be having too much like computational expenditure that's
Right.
unnecessary.
Okay. Let's not get ahead of ourselves. I think I
But
have a
this
good
is a good thing
understanding
to
of
keep in mind that this model has 2 parameters.
Yeah.
GPT-3 has 175 billion parameters.
Right.
And along the way, when we get to neural networks, I'll show you another model that has like about maybe 100,000 parameters.
Right.
And that'll be a good in-between.
Right.
For the
Okay.
two.
That makes sense. I think that it also helps me put in context when I hear stuff like, oh, GPT-4 has 1 trillion parameters.
Yeah. So think of parameter as like the number of knobs that can be turned. Like what are the different things that the model can tweak in the training process? Because all that's happening in like model training is actually that's the next topic we're going to cover is model training. So we talked about parameters. Now next we have to talk about the objective function. The objective function is, so we start with just these data points. There's no line here. We don't know what the line is. The line is just what we came up with as a result of training with a given objective function.
Right.
So in this case, objective function is just what you're telling the AI system to optimize for.
I see what you mean. So the objective function we're using in this case is the price of the home. Another objective
it's not the price. Sorry, price is the output like that you want. The objective function is, suppose I give you like a line that looks like this, okay, and a line that looks like this. How do you evaluate which of those two lines is better at predicting the price?
Well, I mean, the line comes afterwards, right? Like first you plot houses with their number of rooms and the prices.
That's given to you. You have a data set of 10, or let's say you have a data set of 1,000 homes, and you know how many rooms each home has and what the price of each home is. You plotted them on this.
I'm going to draw a bunch of lines and see where most of the homes fit, like which line most of the homes will fit in, and that will be the line that I will use.
So actually just expand that further. What exactly does that mean? Yeah, you draw a bunch of lines. How do you evaluate if one line is better than the other line?
The line in which most of the data points will fit in, like, or coincide.
What do you mean by fit in? Like they'll be exactly on the line?
Or close to the line.
Okay, what if you have a line that say there are like 1,000 data points. You have a line that fits like maybe like, all right, sorry, it's hard to think. Let's think about just 10 data points.
I feel like somehow calculus will get involved here. Like you have to find the closeness of the data points to your line and figure that out for every line, and then finally it'll like be some value which will show you.
Actually, that's exactly it. So it's not how many fit on the line, because there could be some that are just far away. You're trying to minimize the distance.
Right, which is why I said maybe calculus will get involved somewhere over here, because now I'm going back to my high school days.
Absolutely.
Yeah.
So in this case, we use an objective function called mean squared error. Basically, error is basically the distance between an actual home price and the predicted price. What's on the line. That is called the error. So here, error could be like $50. Here, actually, this error would be minus 50. This error could be plus 50. That's maybe plus 10. So actually, the reason we square it is because if you sum up all the errors, the plus and minuses will cancel themselves out, but that's still a bad line. And so what they do is they take a mean squared error. So for each line, you compute the objective function is the mean squared error. So you look at all the errors for each individual data point, you take the square of those, and then you average them out. That's the objective function. And then that's what you can use to, if you draw like 1,000 lines, to figure out which is the best line. So, and then the last step is the training algorithm, which is actually generating this line or this model for you. And actually, the way you phrased it initially is a pretty good way to think about it, which is randomly generate like 1,000 lines and evaluate them on the objective function to choose the best one. But there's a more sophisticated way of doing that, because this process would take like too long if you just generated like thousands of lines. One of the coolest innovations in machine learning is this training algorithm called gradient descent. What it does is, first it plots a random line. It just assigns random values to the parameters. And then it looks at this is where the calculus comes in. It looks at the slope of that with respect to the objective function. and tries to figure out which direction to go in. So it's like, do I go instead of generating?
Oh, I see. Let me finish your thought and see if I'm headed in the right direction. Monica and I do this. If you find it annoying, then we'll because I interrupt her a lot and she's okay with it. So what you're saying is, instead of drawing 1,000 lines and figuring out the line which most closely aligns with your objective function, you draw one line and you move that one line in the direction of what will ultimately be your objective function.
You first draw one line and then you figure out which direction you need to move in, and you keep moving it in that. You shift the here you have only two parameters to play with, so the model is going to play with this. Suppose we call it B and A. It's going to play with B and A, but it knows which direction to move it in to get to a better objective function value. So yeah, it just keeps doing that until...
I'm trying to see why this is needed, because like right now I have an example of like a very simple model. And I'm like, why do you need to go through all that? You just see where the line will be obvious to you, but the line will not be obvious to you when you have an insanely big model.
So actually, even the moment when you have like 3 or 4 parameters, it's already too complex. You can only visualize one parameter.
Yeah, like I don't even know how to visualize.
If there are 2 parameters, if there are 2 features, that's a plane. It's not a line anymore. It's a 3D.
It's a 3D space. And after that, I don't... Yeah, I've seen a lot of videos in like people trying to explain how to think about 4th, 5th dimensions. Whenever I see those videos, I'm like, yeah, that's cool. But like the next day I forget. Like, I don't know. Like my mind can't process more than 4 dimensions. So I see what you mean.
So, and then with machine learning, you get into multi-million dimensions. So this is just a simplified example to understand the concept. But I think the coolest thing is that we have this algorithm that can tell you how to set your parameters such that you'll get to the best objective function value. It'll start with something completely random, and it'll automatically adjust itself until it gets to the optimal value. So that's the cool thing about machine learning. So yeah, I mean, we could go into the details.
I think I have a good understanding of what you mean by models.
It's pretty technical. So I that's pretty much like what classical machine learning is like, and there many different types of like regression is one. There are different tasks you can do. Regression is like trying to predict the price. Classification is another popular task. Classification is like I have 2 classes and I'm trying to predict like orange and not orange, or like spam and not spam, but it's the same general idea.
So that one's classification and this one's
regression.
Regression, where it's not a yes and no, but it's it's a value that you're trying to predict.
The classification has discrete outcomes. Regression has continuous outcomes. So it's like, there's continuous, any real number, between 1 and some
So, but the ultimate objective of a model is to predict something.
Yes, either
depending on the nature of the thing that is being predicted. You have different
types of models,
and the 2 popular ones are regression models
and classification models. Those are not models, there's like tasks. They're the 2 common types of and then there's generation, but that's a new thing. We'll talk about that later. But yes, so you can even think about, we talked about ads, right? So maybe before we get into neural networks, let's think about how this can become even more sophisticated. So what are you trying to do in ads personalization? I am trying to predict for you, for a given ad, are you going to buy this product or not? Or maybe that's too complex, buy or not buy. Let's say, are you going to click on this ad or not?
Predictive, there's something called predictive CTR, like predictive click-through rate.
Predicted click-through rate. So what I'm doing is, it's exactly similar to this. No, I don't have a slide on that, but I have a training data set that has a bunch of clicks, and I have a bunch of characteristics of users. So I'm like, there's a large data set, and I know the label. In this case, the label is like the price. In that case, the label would be click or not click. It's a classification problem. And then I have a bunch of input features, like maybe there's profile information, like person's
demographic
information, behavioral, mostly it's behavioral information, like about what activity they did in the past. And so I
mean, I can already think of like there would be so many parameters that one could gather.
Yes, exactly. Those are already huge. They have several parameters, and what you're trying to do is figure out optimize those parameters to get to a prediction of whether you're going to click on it or not, to optimize for that objective function. So most actually tasks that are used in businesses today are just based on like what I would say is classical ML. Has nothing to do with like generative AI or any of the new stuff. So like ad predictions, like recommender systems, is trying to recommend, which is very similar to the ads use case.
Yeah, no, I mean, I spent the last 7 years of my professional career selling exactly that, like an algorithm which can help you predict if you should be participating in this auction or not, because like most of Google media is sold on auction, and like if the like how valuable is the user and whatnot. So okay, so that's classical ML, like the stuff that I've been selling, or like the technology that I primarily deal with.
Well, it possibly uses neural networks, which we'll get into next. It probably does, or it's not clear. Sometimes they do, sometimes they don't. Maybe with classical ML, it's already good enough. It depends.
Right. Okay, so let's go beyond classical.
Yeah, okay. So let's go to neural networks then. That's the next thing here.